Welcome to our exploration of one of the most revolutionary ideas in physics, special relativity. Developed by Albert Einstein in 1905, this theory fundamentally changed how we understand space and time. It reveals what happens when objects move at extremely high speeds, approaching the speed of light. Throughout this presentation, we'll uncover the surprising and counterintuitive truths about our universe at these extreme velocities. Before Einstein, physicists relied on Newton's view of the universe, where time and space were thought to be absolute and unchanging. Everyone experienced time the same way, regardless of their motion. However, James Clerk Maxwell's equations describing light and electromagnetism created a puzzle. These equations suggested that light behaved strangely when observers moved at high speeds. This raised a fundamental question: what really happens to objects and light when they travel near the speed of light? Einstein's answer would revolutionize all of physics. Einstein built his entire theory on just two simple postulates. The first postulate states that the laws of physics are the same in all inertial reference frames. This means that whether you're standing still or moving at a constant speed, physics works exactly the same way. The second postulate is more surprising. The speed of light in vacuum is constant for all observers, regardless of their motion or the motion of the light source. No matter how fast you're moving, you'll always measure light traveling at the same speed. These two principles alone lead to all the strange effects of special relativity. The speed of light, denoted by the letter c, is exactly 299,792,458 meters per second. This is the universal speed limit of our universe. What makes this speed so special is that it's the same for all observers, no matter how fast they're moving. Unlike everyday speeds that add together, the speed of light remains constant. If you're moving toward a light beam or away from it, you'll still measure the same speed. Nothing with mass can travel faster than light, and this cosmic speed limit has profound implications for space, time, and energy. One of the most fascinating consequences of special relativity is time dilation. The equation delta t prime equals gamma times delta t describes this effect. What this means is that moving clocks run slower relative to stationary observers. If you could watch a clock moving at high speed past you, you would see it ticking more slowly than your own clock. Time itself is relative to motion. The faster an object moves, the slower time passes for it relative to a stationary observer. This isn't an illusion or a mechanical effect. Time genuinely passes at different rates depending on motion. This has been confirmed by experiments with atomic clocks on fast-moving aircraft and satellites. Alongside time dilation, special relativity predicts another strange effect called length contraction. The formula L equals L sub 0 divided by gamma tells us that objects contract in the direction of their motion relative to moving observers. If a spaceship flies past you at near light speed, you would measure it as being shorter than it would be if it were at rest. However, from the perspective of someone on the spaceship, everything appears normal. They would see you and the space around you as contracted instead. Like time dilation, this is a real physical effect, not an optical illusion. Objects genuinely become shorter in their direction of motion as their speed increases. The key to understanding all relativistic effects is the Lorentz factor, represented by the Greek letter gamma. The formula is gamma equals 1 divided by the square root of 1 minus v squared over c squared. This factor appears in almost every equation in special relativity. When an object is at rest, meaning v equals 0, gamma equals 1, and there are no relativistic effects. But as velocity v approaches the speed of light c, gamma increases dramatically, approaching infinity. This explains why time dilation and length contraction become more extreme at higher speeds, and why it's impossible to reach the speed of light. The Lorentz factor quantifies exactly how much time dilates and length contracts at any given speed. Perhaps the most mind-bending consequence of special relativity is the relativity of simultaneity. This principle states that events that appear simultaneous in one reference frame may not be simultaneous in another moving reference frame. Imagine two lightning strikes hitting the front and back of a moving train at the same time according to someone standing on the ground. To a passenger on the train, these same events would not occur at the same time. One would happen before the other. This challenges our everyday notion of a universal now. There is no absolute simultaneity in the universe. Whether two events happen at the same time depends on the observer's motion. Einstein's most famous equation, E equals mc squared, emerged directly from special relativity. This formula reveals that mass and energy are interchangeable forms of the same thing. A small amount of mass can be converted into an enormous amount of energy, since the speed of light squared is such a large number. This principle is the foundation of nuclear energy, both in power plants and in weapons. It also explains how the sun and other stars generate energy through nuclear fusion, converting a tiny fraction of their mass into the light and heat that sustains life on Earth. This equation fundamentally changed our understanding of matter and energy. Let's recap the key insights from special relativity. First, space and time are not separate entities, but are interconnected as spacetime. Second, the speed of light is the cosmic speed limit, constant for all observers and impossible to exceed. Third, time is relative to motion. Moving clocks run slower, and this effect becomes significant at speeds approaching light speed. Fourth, mass and energy are equivalent and can be converted into one another according to E equals mc squared. Special relativity revolutionized our understanding of the universe at fundamental scales. It's not just abstract theory, but has practical applications in GPS satellites, particle accelerators, and our understanding of the cosmos. Einstein's insights continue to shape modern physics more than a century after their discovery.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.